All right, so sorry, I decided to switch up my talk at the kind of the last minute because I didn't realize I was speaking in front of everybody, not just people who like to hack on the compiler. And I found it very difficult to create an exciting presentation about expression trees. I don't know, you might have other opinions. But I decided to switch the topic a bit because over the past year that I've been working in the Julia group, this is one of the major new features of 0.4 is stage functions. And it's probably the thing I get asked about the most. What exactly are stage functions? And how are they useful? And why are they different than what we've had before? And I think it's actually very easy to understand what they are and how they're useful. But it takes a little bit of wrapping your head around this, like what's actually happening under the hood. So I think what I'm going to do is going to just motivate what stage functions are broadly, just give some simple examples, and then just show you actually how they're implemented. And I think this will be really beneficial for people who maybe don't look at the compiler, don't care. It's actually, I think this is one of the amazing things about Julia is that around this time last year, we actually implemented stage functions during JuliaCon. Sketched them out at least, with mostly Keno did it, and Tim Holy. And Tim Holy was just the motivation because the guy's so excitable. But and it was just so remarkably easy to hack this in that it kind of at that point just really showed the power of the design of the language and the compiler and the simplicity of things. And you can do something this powerful that really only exists currently in research languages like Meta ML, for instance, or Scala, with these annotations, with these fancy library JIT compilers, and it just was really great. And I think it will just show you that maybe approaching these types of problems in the compiler is not as hard as you think, and so I just hope it'll be a little bit, and what I'm going to show is not going to be very complicated examples of stage programming. I mean, you can obviously go crazy with it, and Tim Holy has. If you look at his code over the past year, it's now leaking its way into all the array code basically, but I think just a simple understanding of the model and how things work will be beneficial, and hopefully some warnings about what's dangerous about them, and be wary. Just like with macros, you shouldn't abuse this stuff. You should know what you're doing, but it's fun to play around with. So with that, let's just start. So I already talked about this, and so we implemented this in an afternoon, but it really took about a year for all the bugs to be worked out. It's actually not very much code, but it caused a lot of headaches in terms of what we were actually going to support and how it actually works in practice. And I think it was very non-obvious what the bugs actually ended up being. And it took a long time for it to work through all the different stages of what stage functions actually are. So it's one of these things that looked innocuous in the beginning, and it was like, oh, this is going to work really quickly, and then 6 months later, we're still banging on it, like trying to get it to work. So, but now they're used out throughout the array code base, making your new fancy, more abstract arrays much faster. So you should thank Tim Holy and Matt Bauman for their great work on doing that. So we're just going to talk quickly about what is stage programming, what kind of examples of stage programming you can do in Julia, why is it useful? I mean, it's showing up everywhere. There's more places where it could show up, so we're going to talk a little bit about that. And how do you use it? Hopefully we can do some really simple demos in the REPL to just kind of motivate how you can actually do this in a couple lines of code. And we'll talk about the downsides of stage functions, because there are many, and I think some future directions about where this kind of stuff can go will be great. So what is stage programming? Stage programming is really any type of implicit or explicit dynamic compilation or static compilation in your program at fixed points, right? So it could be macros expansion, it can be code generation, runtime code generation. It actually takes on a lot of forms, and we've actually had stage programming in Julia for a very long time in terms of in form of macros, right? Macros are a form of stage programming. They just happen at an earlier stage in the compiler pipeline. The new fancy stage functions that we have in 0.4 come much later, and you'll see the trade-offs that you get with each of these. So Julia's compiler is an example of stage program, right? I mean, you have explicit phases in the compiler, you have your parsing, you have your macro expansion, you have your type inference, and you have your code generation. And since stage programming is a lot about runtime code generation, at least in the Lisp tradition, mostly it takes the form of at what point does the macro expansion actually, the staging actually occur? So traditionally, in traditional Lisp systems, you mostly got macros, and macros are obviously incredibly powerful. If you've ever seen, like Common Lisp or Let over Lambda, if you read that book before, I mean, you can do just amazing things with macros. But they are quite, in terms of the compiler pipeline, they're quite early in the stage, so you don't actually have a lot of semantic information about your program, right? So how many people have used macros before, know what macros? Can you just a raise of hands real quick? Wow, almost everybody. Wow, good job, Jeff. I mean, it's kind of crazy that this many people have used them, right, and so seamlessly, because it's usually considered like a hard feature of traditional Lisp. But so who's aware of the problems of macros, though? Like, who's ever tried to written their own macro and tried to make it work? Yeah, it's really, really difficult, right? Because there's so many edge cases, and you actually don't have a lot of semantic information about your program. And what you really want to do is rearrange the order of execution of your program. But all you have is symbols and abstract expressions that you don't know anything about, right? And you have limited semantic information in terms of literal values that we carry through the AST, like numbers, for instance, or range expressions that have constant values and stuff. But you're very limited, and I think this shows up a lot when you want to do fancier type things. You can do them, but it ends up being kind of a hack. And I don't know if you're aware, but back in 2012, Jeff actually posted the very first stage function implementation entirely done with macros. And if you just look at this thing, you're just like, how did this ever come out of Jeff Bezansen's head? Because it's just like the antithesis of everything he stands for. So maybe we should actually have a look, because it's kind of fun. Yeah, it's really cool, though, because it shows you that you can actually do these types of things even with a very limited or a more limited system. Let me see. Sorry, I have so many windows open at this point. I really should just have had this open. Is it this? Oh yeah, here it is. Updated to work on 0.4. So as you can see, this is the first incarnation of stage functions in 2012, and so it took, out of Jeff Bezansen's proposing, like, oh, this is cool, you can do this kind of stuff in 2012. It took until 2014 for it actually to be implemented in Julia, right? So sometimes these ideas have a long gestation period in terms of, like, especially with stuff like what Jeff talked about today. It's really great, and it gets people excited, but sometimes you have to wait a little bit. So just be patient for some of this stuff, right? But as you can see, it's basically taking an expression here, and one of his original motivations for, and this is what is used a lot in the array code, is to do like loop unrolling, right? So you basically want to amortize the cost of iterating through loops, and so you can do a better job if you partially unroll some of these looping constructs. But you can see the macro here is basically taking an expression and making sure, you know, it's well formed and getting its argument names and basically, you know, creating some symbols here. And then it's creating all these crazy globals and locals and inner functions in this let block. And then it's going to go back up here and actually inside the macro, it's call eval, which is always bad. And but it creates basically this stub function that you can call and kind of basically creates the function that you actually later call with the actual values, right? And this is basically the whole idea around stage functions in 0.4 is that you actually are calling the function not with, you know, a symbol or an expression like you would a macro, but you actually have the value and type information at that point. So it's actually a lot more semantically meaningful if you're trying to do the transformation if you have access to this information. So that was cool, and there was a lot of talk about, you know, how this was going to change everything in Julia, and I think people were kind of unsure about where it fit in the whole scope. So it's just an interesting bit of history. So the key difference with the implementation that we have now in 0.4, the pre-release, is that, you know, stage functions, or I guess they've been renamed generated functions. I really don't like this name, but are invoked at a later stage in the compiler, and they're invoked during actually during type inference. So as type inference is going through your code and figuring out, you know, through data flow, you know, what the actual types are, it actually can invoke, you know, the staging method or the method that generates an expression or another bit of code, the code compilation unit, and it basically is giving it types at that point, and it can basically call this thing multiple times during type inference, because sometimes type inference takes multiple runs, right? It doesn't always run just as a single pass. And basically what it does is it gives the function, you know, access to your type information at that call site, and you can basically use that type information to generate code specifically to that type that you matched on in your function. And so since it's at a later stage in the compiler pipeline, you have a lot more semantic information at this point, right? And that's really the key idea here is that the later you push back your code generation stage in your compiler, the more and more semantic information you're collecting about your program. And so I think this is a really awesome, opportunity in terms of like what Jeff showed today. You know, we're hopefully in the future going to collect, you know, maybe product types or do higher order analysis, right, on Julia programs. So we're going to collect an amazing amount of information. And we have a seamless way of actually, you know, taking all that information and doing code gen on, you know, not only the type of your arguments, but maybe other information about your, you know, program at that point, right? Which is very exciting because not very many people or any people, to my knowledge, have really done this to this extent before in a language that, you know, allows users to do this very easily. So we talked about this. So I think we should just dive in and let's look under the hood here.
Can you give an example of writing the stage function?
Yeah, that's when we're going to do this. It's going to be REPL time. So the current syntax is basically looks like this. You basically put this generated macro annotation here, and you have to do function foo, right? And then we're going to show what x actually is, right? And then we can basically say, so every stage function has to be a pure program, right? So basically every input that you give it in terms of types, it always has to return the same output. So that's very important. And then the output it returns is actually an expression or a quoted expression, right? I like this example because it shows the phasing that's going on. Just it's very simple, right? So if we call foo with 1, so who knows what x is going to be? What is it going to show? Is it going to show the value or is it going to show the type? It's going to show the type, right? Because at the point of when foo is called, it's actually being called as types as its argument. So x is going to be bound the type of its argument and not its value, right? So you can see that. Now if we call it again, it's actually cached. And this is very important because you don't want to keep on recompiling and regenerating the functions over and over again. And this was an early performance problem when we first implemented this in terms of, it would just basically generate the same code over and over and over and over again. And it's also important for recursive definitions, right? Where you want to have a stage function that calls a stage function, basically. And you need the ordering to be correct so that the staging happens correctly. But if we call this with any integer argument, it will basically, right, it basically is, oops. Oh, I gave it an int, sorry. Yeah. So this is just like the most bare bones example you can possibly have. I think another interesting example to look at would be a fixed sized array, right? So if you wanted to do we're going to do static vec of type t and of size n. We want n to be integer. Vals is a vector. Oh, what do we got here? We'll just cheat. Okay. Right. Oh, did I screw up? Where did I screw up? Oh.
You can't do that n subtype.
No. We can't redefine types either, right? Okay. Okay, so we get a static vector type here, right? And it's just basically what it's doing is it's lifting its part of its information about its representation into the type system. So it's basically just saying that it's a length 3 static vector, right? And with a stage function, we could trivially get its length without even having to call anything, right? So that's something that's cool about
Static vector.
Yep. So if we look at the code here, so it basically just gives you the result right back, right? So it's perfectly inline result. And so this is just another simple example of basically you can use the generation capabilities to basically return you back something with no computation. And so this is really what the whole idea of the generated functions are, is basically a way of, or a performance way of doing some partial evaluation of your result, right? And so this is a user-definable way of doing it. So you could actually, trivially do this without generated functions, but it's just a good example of using it. And so you can think about if you have static vectors or something like this, right, that knows the length of the array and the array type, you can basically start to generate code based off the array size. And so you could special case, the smaller arrays to do very efficient computation, right? Very efficient dot, very efficient add, multiplies, and stuff. And so this is just a couple simple examples we have. And people have talked about doing static arrays in Julia for a while. And I think the stage functions will really enable an efficient implementation of these ideas, especially for smaller matrices. It's just something that it was missing before in terms of being able to have hooks to be able to elide some of the overhead. So how am I doing on time? Does someone know?
15 minutes, including questions.
Okay. So this is the main entry point to the basically staging and type inference. And so you basically see the stage cache here. And it's basically what it does is it saves the environment state, which you can see here, which is the method, the arguments that the method is called with, the type arguments, and it's a local environment. And it's important to do this because basically if you don't save the environment, you can get into trouble where you basically call the stage functions in the wrong context, and you basically save a result that you shouldn't. But basically, every method now has an isStage field, and the isStage field basically is just a flag that we set through the macro annotation that the method is staged and should be handled especially in the type inference code. And so if it's not this stage, you just return the function's regular code. But if it has the isStage field and the stage method is in the cache, you just return the code that you've already generated right upon instantiating the stage function in the cache. But if it hasn't been cached yet, you basically check to see if the types are leaf types. And this was an issue before where we were allowing abstract types to basically permeate through to stage function expansion. And this was thought to be a useful feature, but it ended up really causing a lot of issues, which are linked above here. And the main issue is that you can't guarantee that non-leaf types behavior is monotonic because you don't have the whole. You can't assume that the types that you generate the code for, you basically subsume all functionality of all possible subtypes at that point, right? But so the main entry point to the C code is basically called here. So if it is a leaf type, so say you have a stage function that's like an int, for instance, then you call the instantiate stage method. And the instantiate stage method is basically going to take the method, the arguments that you passed it in the local environment, and basically do the macro expansion, have a hook back into the macro expansion step to basically go all the way back to macro expansion to expand out the code that you've basically quoted in there, run the function, and basically splice it back into the regular function. And then you're going to recall that function with the actual arguments, right? So if we have a look to what's going on here. It's in source. So this is the actual instantiation method that's in the current general function code in C. But basically, as you can see, it's actually not very long. And what we're doing here is basically looking at the functions, the methods, AST, and if it's the old AST, we're basically trying to uncompress. So sometimes, in Julia, that the AST is compressed for efficiency reasons. So if it is compressed, we're just going to uncompress it right here. And we make sure that we're basically going to build up an anonymous function, right? So we create basically an expression with an arrow type. And then we're going to basically start pushing all the old arguments into the arrow type as arguments of the anonymous function. And then each of these are basically building up a colon, basically a type assertion expression. And we're going to put those in as the arguments to the function. And then basically dot the result so that we get the splatted arguments. And then basically all we do is we basically just eval it back into the module in its context, right? So it's basically you run the function, you generate the quoted expression, and then you basically now that function is cached through Julia's generic caching mechanism, and then you basically can now call it after you exit type inference with the values just like you would any other function. And the function basically gets specialized to the expanded version that you either have in the cache or you've just expanded here. So we can kind of see how this kind of works if we look at the actual environment here. Where is it? So if we call foo with its local environment, this gives you back the method table. Right? And so the method table could have multiple functions in it that are either staged or not staged. So each method in the method table has the flag that basically says whether it's a staged function. But here foo only has one method, so it will be staged. So we look at the first, and the method table is a linked list. Defs. And so its first argument is basically a method here. So we have our method. And we can look at the field names, right? And we can basically tell that it's a stage method. So it's true. And then we can get the function argument of this method. Now we have the anonymous function, and then we can get the code for this anonymous function. And this is the actual function that gets generated during the whole generated function stage. And you can see here that it's basically just creating a lambda where you basically take x because we were going to show x, and this is the value of x that we propagate through. And then we're calling show on the x type that instantiates the stage function and not the actual value that gets spliced in. And this is the actual expression that's going to get spliced into the resulting function. And you can basically actually call this, I think, is it this? Nope. So this is the function argument. And if we go def, is it this? Yeah. So you can actually call this function directly, the ungenerated function, basically, and you can see that it takes the basically type as the argument, but then it passes the result, and it basically just splices it in. So this is basically how the whole system works, and you can do a lot of cool stuff with this. And if you look in the base code, you'll see a lot more sophisticated examples about using this for doing code generation for arrays, and it's showing up sometimes in the iterator stuff now. And I think it'll show up in a lot more examples. But it's actually very simple how it works, right? You basically, it just works just like a macro, but you're calling it with the types instead of the expression, and it happens at a later stage in the compilation pipeline. And since it propagates the types, you have a lot more semantic information, because it's very natural in Julia to basically encode the semantic information of your program into your type system. And since we can have parameterized types, that are arbitrarily nested, or you can compose types together, you can shove a lot of information into the type system, which you can then use to instantiate code, arbitrary code. And if the type inference is able to figure out the exact type at that definition point, right, it can actually statically just basically have a static lookup of the function, and it doesn't have to do dynamic lookup of the resulting function. So it's a lot more efficient in many cases. And so Kenno is going to probably talk a lot about this today, because he hacks to death this capability to shove all sorts of crazy information into the type system to do crazy metaprogramming type stuff. So let's just talk about some of the difficulties with stage programming. So, I mean, the real obvious one that seems to come up into the discussions about this is that people have a hard time reasoning about what things get staged, when they don't get staged, because it really deviates from the simple imperative model that you have of programming, right? And so the reason is that basically, it calls back, it's generating functions that basically go back into the compiler and reinstantiate code, which could go arbitrarily back before it actually expands to some fixed point. And at that point, the control flow is a little obscure, and it can get some kind of crazy sometimes, tracing through the whole execution history of how the program actually gets generated and what code you're actually running for some of these stage methods. It relies a lot on the stability of inference and inlining for predictable performance. I think we're seeing this sometimes when the heuristics change a little bit and performance drops, or we're not quite sure why things are slow and why they're not slow. Because if you're relying a lot on the static compilation to basically do inlining, then sometimes, are we done?
Yeah.
Oh, sorry. Okay, and basically, an advantage of the system is that you could basically still retain whole program static compilation, because since you're doing it at type inference time, if you have concrete types, it doesn't prohibit you from doing static analysis. But the problem is that people are starting to lift values into the type system, and these can be runtime values, and that kind of defeats the whole ability to do static compilation with this type of system. So I think it's being a little bit abused, and might have to pull back a little bit on the expressiveness of what we allow it to lift values, arbitrary values into the type system, because otherwise, the whole static compilation of Julia programs will be much more difficult. So, all right. So if you have any questions, sorry guys, I went a little over.
We thank Jake. Take 2 or 3 questions while Leslie gets set up. No questions?
Yeah, John.
I guess I'm wondering, do we think there are possible extensions to stage functions?
Oh yeah, I mean the obvious one would be staging on values, right? But as Jeff said, it's really difficult. And another point you could potentially do staging. I don't know if it's quite considered staging in the classical computer science senses. You could do pattern matching, right? And and we already do this for some local rewrite rules for some of the linear algebra code, and that could be more expressive. And we could have hooks into that to latch on to specific patterns that you match on in the AST and do local rewrites of that particular pattern. I mean, there's whole programming languages built around this concept, so it's pretty interesting.
Context where I just don't understand whether it's technically feasible is whether you can stage on the returns of functions. So you could say this function is inherently type unstable, but likely it's going to have its result used in a lot of computation afterwards, and so you should stage everything in a body afterwards.
Oh yeah, I think this is really useful in linear algebra type situations where you want to run like a huge like linear algebra code, right? But you don't necessarily have a good understanding of a type stability in your program. And I think that will come with selective value types that you can stage on. I mean, that's to me would be the most natural solution there. But like you said, I mean, if you have arbitrary staging or code generation, you can get into trouble really quickly. So it has to be limited, and it has to have a same model of, you understand what's getting staged and what's not. Yeah, I think the other thing is like, I think we'll show up in any type of trait-like system that we see in terms of actually making it efficient. So, all right, here you go.